The topic is self-lensing binaries, and self-lensing flares in particular is what we want to find. And I'm going to show you how to find them and how not to find them. So first thing we need to talk about is what is actually self-lensing flares. So self-lensing, what we're talking about is actually gravitational lensing. So in general, when there's a very massive body and behind that body there's a source of light, then you would get what you call gravitational lensing. That means that just like if you have a glass lens, that the light passes through it and it focuses the light to you, what you would see is instead of seeing a light source that is very small, you would see a light source that's a little bit bigger. Depending on how massive the lens is and what the distances are, it's kind of, there's a little bit of geometry that goes into it. But in the end, what happens is that the star or the galaxy, whatever it is you're looking at, gets bigger. Looks bigger, it can get warped sometimes, and it gets brighter. Now, sometimes you can see galaxies or galaxy clusters that are very, very massive, and they will lens galaxies in the background. You can see multiple images of those galaxies, and that's what we call strong lensing. Sometimes you have inside our galaxy, you have stars or black holes or any kind of massive object, and in the background of that star, you have another star. And in that case, the background star, which is lensed, will actually become a little bit bigger and a little bit brighter, but you don't see it. You cannot resolve it with most of our telescopes. So we call it micro lensing because the typical sizes are micro arc seconds, and you cannot actually see that. But because the lensed object becomes bigger, it gets brighter. So this is what we call microlensing, and it's a way to detect massive objects in our galaxies, like black holes, for example, that a lot of times if the black hole is not orbiting around something else, and you cannot see it, you cannot detect it. But when the black hole comes just randomly in front of a background star, it will make the star brighter for a few weeks, and then it will decay back into its normal brightness, and you can say maybe this was a black hole. That's what we call microlensing. And it's based on just random stars and massive objects in our own galaxy. So the case for self-lensing flares is a little bit different. In this case, what happens is you have two stars orbiting each other, and one of these stars can be a black hole or a white dwarf or any sort of massive object. And then because they circle each other, and if you're lucky and the orbit is edge on, then you actually see a lensing effect just because the massive object comes between you and the other star, and the star will get brighter. So there's a big difference between these two things, between the microlensing, the classical case of just random things in our galaxy, and the self-lensing case, and we'll talk a little bit more about the differences. So here we see an example of just a simulated event. A lot of the time I invested is in writing a simulator that will tell you what the brightness of the star will be as a function of time, what we call light curve. And as you can see here, this is the time scale in seconds. So you see that the event itself takes about 1,000 seconds. So much shorter than what you have in the galaxy, where stars are just moving in space randomly, and they move pretty slow. The angular distance between them is pretty slow. So, the angular velocity is pretty low. And then this sort of event can take weeks or months. And in the case of self-lensing, because the objects are very close to each other and they're orbiting, then the flares are weaker and they're faster. So as an astronomer, you would say, well, if the flare is much weaker and it's also much faster. Okay, so as I was saying, these are very short flares. They take between a few seconds to about an hour, depending on the parameters of the system. And a lot of times these flares are not going to be super bright. So they can be either, in best case, you will magnify the star by a factor of 2 or 3 or 4. And in most cases, you would magnify the star by a few percent. So in this case, this is a pretty good self-lensing flare. The magnification is 1.4. So that's pretty obvious when a star gets brighter by 40%. But a lot of times it will get brighter by a few percent, like 3% or something like that, depending on the parameters. And here you have kind of the cartoon of the system. So it's two white dwarfs in my case. And these are just very compact objects. It's an object with the mass of a sun that's burned out all its nuclear fuel and collapsed to the size of a planet, basically, of planet Earth. So a few tens of thousands of kilometers. So you have one white dwarf and another white dwarf is a little smaller and more massive. It comes between us and it will lens the bigger white dwarf and make this bright lensing event that lasts about 1,000 seconds. So, and you can also see from the duty cycle, which is a very, very important characteristic of the system, the duty cycle is 1 over 1,600 or 1,700. So just the chance that you will see this system, if you're randomly looking at it one time in the sky, the chance that you will see it while it is flaring is actually very low. It's less than 1 in 1,000. So most of the time it's quiet. And only when the thing moves right in front of the source, then you would see the source get brighter for a very short period. So this is already something very hard to find, because most of the time you're not looking at these objects all the time. You're observing parts of the sky, once per 3 nights, once per 10 nights, depending on which survey you're doing. And then the chance that you will just randomly see them is very low. So this is already the first challenge. So this is kind of what I was talking about, the differences between classical microlensing. So what we have is that in case the source is a big star, like our sun, and the lensing object is, for example, something with the same mass as the sun, like a white dwarf, even if it's small, then the size of the Einstein radius, which is basically typical size of the lens of the gravitational effect, is the size of a planet. So it's basically the size of Earth. So it's 100 times smaller than a solar type star. So that means that if you have a very small lens crossing in front of a regular star, what we call main sequence star, like our sun, the effect is going to be tiny. It's just the difference in radii is just going to make it so, it's 1 in 10,000 magnification. You're never going to be able to see it unless you have very, very high precision, like the Kepler telescope, which had the ability to see things that are very, very small changes in the light pattern. And there is actually 5 cases of main sequence stars that are self-lensed by another object in the binary with a star, white dwarfs in that case. And all of these 5 events are in Kepler data. So if you don't have the data that Kepler had, which is very high precision, you want to use other sky surveys, you have to have a source that's a lot smaller. It's on the same order of magnitude of the size of the Einstein's lens. So you want to look for bright objects that are the size of Earth-sized planets. So we're talking about white dwarfs, basically. That's the topic that I'm working on, which is white dwarfs that are being lensed, so they are the light source. And the thing that is lensing them could be another white dwarf or more massive objects like neutron stars or black holes, which still have a mass of one sun or a few masses of the sun, but even smaller radius. So for example, a neutron star would be 1,000 times smaller than a white dwarf, and a black hole is about the same size, a little bit smaller than that. So they're very dense objects. So these flares are short, they're not very strong. Why should I even look for these things? How is it do we have even a chance to figure out what they are? And the upshot is that these, because they're orbiting each other and not just flying through space, then these are not one-off events, they're periodic. So if you identify a system, or if you think a system has a self-lensing flare on it, you can observe it, and then after a few weeks or a few months, when it comes back, you will see it again. You wait a little bit more, you see it again. So if it's not a very, very long period of, like 10 years, then you have the ability to actually look at the system again and again and figure out the period, and then you know exactly what you're looking at. And in classical microlensing events, you see the object, but except for the fact that it gets brighter, you don't have a lot of information. So you can try to estimate the mass and stuff like that, but there's a lot of unknowns. In a system like this, if you identify it, you have the ability to know everything about the system. If you take some more data with other instruments, you can figure out exactly what the masses are, what the sizes are. You can figure out everything about the system. So this is a really good way of figuring out systems of binaries with compact objects like white dwarfs and black holes, which are relatively not well known. So why is it interesting? So like I said, they're periodic. So this is what we call gold-plated events. If you find one and you see that it's periodic, you see something flaring every 3 days, then you know exactly what it is. You cannot confuse it with anything else. There's nothing else that looks exactly periodic like this in this way. Because the orbit has to be edge on, then you also know, if you measure, for example, the velocities using spectroscopy, you also know the masses, because now you know the velocity and the distances and the periods, so you can use Kepler's laws to solve everything. Whereas if you know the system has some inclination and you don't know what it is, then there's some uncertainty about what the mass is, because it's a different mass if it's edge on or if it's like this. If it's like 45 degrees, it will be a different mass. So because these systems have to be edge on, then you already know a lot of information starting up. You can find white dwarfs where we don't have a lot of information. So for example, we know about white dwarfs that eclipse other white dwarfs. So that means that the white dwarf is so close that it hides the light of the star. And if the white dwarf is very close to its companion, then the eclipse that makes the light weaker will actually be much stronger than the lensing effect. And then you don't see a lensing, you see an eclipse. So you see light going down for a little bit and going up when the white dwarf is eclipsing. And we know there are systems like that, but those are only systems that are very close together. And we know about detached white dwarfs that are very far away from each other, like a few year orbits, but we don't know the middle part of the white dwarf distribution. And this could be a way to measure some of these white dwarfs in the intermediate orbits. If you find a white dwarf with a black hole that is orbiting and lensing it, that's even more interesting because we don't know anything about white dwarfs and black holes and binaries. We've never seen any of them. And we don't know anything about the population of black holes and neutron stars, or we know very, very little about them. Another thing is that these self-lensing flares are in the range where these white dwarfs are so close to each other that during their evolution, they must have become a red giant. So a regular star will go through this phase of being a red giant and then shrink down into a white dwarf. And during that part, the two objects in the binary, in the self-lensing binary, are, in most cases, they're so close that they had to have shared the envelope of each other. So they used to orbit each other inside the envelope of one of them, or in two separate stages. And right now, all the models that we have about common envelope are very, very are not well constrained. So that means we don't know what actually happens. And if we find a few of these systems, that can help us figure out how these objects survive the common envelope, what kind of distance they have when they exit this phase, how fast is it. So this can be really gives a lot of information about the common envelope. Another thing that is useful is that people are looking for double white dwarfs that are close to each other so they can produce gravitational waves. And if you know the properties of the system, you can use that to calibrate gravitational wave detectors like LISA that there's planned for the next decade. So there's a lot of really useful information, a lot of really good reason to be looking for these systems. And this is kind of a roadmap that we've come up by just running many, many simulations. I've done a lot of simulations of different objects with different masses and figured out kind of what would be the intensity of the flare, kind of to figure out if it's detectable. So here, the y-axis is the magnification, how big the flare is going to be. And these dashed lines, dashed horizontal lines, are kind of my guess of how sensitive our telescopes can be. So the bottom line is for very, very sensitive telescopes, and the top line is kind of more realistic. So you can kind of think that everything above this line is detectable. And you can see that for different periods, different kind of masses of objects. So these are white dwarfs orbiting white dwarfs, and these are neutron stars and black holes orbiting white dwarfs. They are more massive, and the mass goes up as you go with this plot in this direction. And you see that kind of this tells you which periods you can actually find and which periods are too weak to find. And I think this is a very useful result because it helps you focus when you're doing the search on what you can find, what you can't find. And these little rectangles that I put here are the duty cycle. So that tells me that if you're looking for a white dwarf with, 0.6 solar mass, which is the orange one, and you're looking for being just on the detection threshold, then you're looking for an orbit of a few days. That's this axis. And you're looking for something that has a duty cycle of 1/1500. So again, that means that unless you take 1500 images of this object, you're not going to find it during the flaring event. So you need lots of repetition, lots of repeat on every white dwarf. And it also means, by the same geometry, it also means there's only one out of 1500 probability that it would be edge on enough for you to see it. So you're going to need to observe 1500 white dwarfs and observe them for at least 1500 times each to have a probability, like a probability that's average probability of seeing one of these flares. So you can see that the odds are kind of stacked against this project. And this is kind of an explanation for what I said, is because the parameter space that you have goes both in time when you're orbiting, so you have to hit it at the right time, and it goes in angle. You have to find one that's the inclination of the binary is such that it's edge on, and that kind of defines for you a circle that gets smaller the further away you get from the binary. So this kind of explains that if you look at binaries that have a big separation between them, then the chances that you will actually see something, one of these flares, as you can see here, the duty cycle goes down the more you go to wider orbits that are that have longer periods. That means higher separation. That also means the duty cycle drops off. And if you look for black holes, for example, the black holes already have a duty cycle which is 1 in 30 or 1 in 10. So here the requirement, because these are very short orbits, 1 minute orbit or few minute orbits, these are really extreme objects that are orbiting each other really closely. Those ones actually you don't have to be so lucky to see it edge on, so you have some advantage, and it flares a lot of times. So if you observe it for an hour, you'd see a bunch of different flares. You'll definitely know to identify what it is. So that already tells me from this roadmap that white dwarfs are a harder target to hit than the black holes and neutron stars. Right, so this is kind of the state of the project. I mean, here you can see some of the tools I used for the simulation. So this is code that I wrote to actually simulate for each geometry where you have one mass and another mass and the distance between them. You can kind of see the shape of what the star would look like after the lensing. So this kind of warps it and changes its shapes and increases its size. And then you just calculate how much surface area you have, and that tells you the brightness of the flare during that period in time. So we have kind of a simulator that can make these light curves very quickly. We have simulated surveys, so we take different telescopes that exist or that we know that are going to come online soon, and we simulate what would happen if you observe the sky for a few years with each survey and how many of these events you're going to find out. Yeah, there's a lot of other things that I'm still planning. Right, so what is the prospects of actually finding these things? So this tells you the effective volume, so how much space is covered by a different surveys. And this dashed line tells you what is the best model that we have for the number of double white dwarfs in the area of our solar system, or in the galaxy in general. So it's 1 double white dwarfs per almost 2,000 parsec cube. So they're not very rare, but they're also not very abundant. And you can kind of see that with TESS, which is a satellite that's used for finding planets, because they just don't go very deep. They don't have a lot of white dwarfs covered. You see that the effective volume is much lower than the density of white dwarfs. So it's kind of hopeless. Curious is a satellite that we're working on that I'm involved with here in Berkeley, that they want to build an array of satellites that will take many, many images of the same piece of the sky with high precision. So that's a very good satellite for doing that. And you kind of see that with a single object, with a single satellite, those are small CubeSats, you can't do much better than TESS, even though it's funny because TESS cost NASA, I don't know how many millions of dollars, and this Curious thing is sort of something we're building on very low budget here in Berkeley, and they want to actually make a fleet of 400 or 900 of these. And with the Curious array, which is the red line, I think this is for 900 satellites that cover the entire sky at the same time continuously. Then you start to see that there's enough sensitivity to find some of these white dwarf self-lensing flares. Because you're observing all the sky and observing it continuously, you get a much higher probability of seeing one of those very rare flares. And with LSST, which is the green line, which is just the biggest survey that's being built right now on the ground, of course, this is just a super survey. It's going to do everything much better than anybody ever, it's like the Superman of surveys. So of course, if you calculate how many of these events will be found by LSST, it's pretty high. But the problem with LSST is that it will take an image of the sky once every few days and then come back to it later, a couple of years later or something. So it will be very hard, even if just randomly there's going to be so many white dwarfs that you're going to see some of these flares. You will probably see, in the survey, you'll see one measurement is higher than the others, and you will not know what it is. It could be an asteroid, it could be a satellite glint, it could be a bunch of false positives. And if you don't get this continuous coverage where you see the same white dwarf flaring many, many times and you can figure out the orbit, it's going to be very hard to even know that what you're looking at is a self-lensing flare with LSST. So LSST is kind of like, it's going to be easy to find these, to detect them, but it's going to be very hard to identify. All right, so finally, for double white dwarfs, the conclusion I got after working on this for a year is that it's probably going to be hopeless unless you get to something like LSST, just because we know that there are a few eclipsing white dwarf binaries. And if you look at the distribution, the expected distribution of how many double white dwarf systems there are, if you split that according to the separation between the two objects in the binary, then you see that for eclipses, there's a little bit more objects as you go up and up and up. And then at some point, when you reach a period of a little bit less than a day, where you actually get sensitive to self-lensing flares, and the eclipses turn into flares. And when you look at that, actually the number of white dwarf goes down very fast. So, and this is if you include the parameter space that you need to be inclined in the right way, and you need to hit it the right way, just, the numbers just go down. So if you have a few eclipsing white dwarf binaries, then the chance that you will find some of these binaries where you're actually sensitive to them is just immediately goes down. So using the same surveys where we found, I don't know, like 10 or 15 eclipsing white dwarfs, you will probably not see any self-lensing flares. You need a bigger survey. And this is sort of a cautionary tale, because I could have known all of this from the start if I had looked at the actual distribution of these objects, and if I done all the back of the envelope calculations, and if I had figured out that the eclipsing binaries and the self-lensing binaries are sort of similar, only different places in the parameter space, I would have been able to say, well, this is hopeless with the surveys that we have, even before running any simulations. But the fact is that I didn't know much about self-lensing or microlensing in general, and kind of I wrote a simulator, so now I know about microlensing, and I have this roadmap of the parameter space. So now I know that the parameter space is only interesting in this and such separations. And so I feel like doing all this work to find out that I can't find these systems with the current surveys, it's kind of helped me figure out how the parameter space looks enough so I can do these simple calculations in the end. But it's not all hopeless. What about white dwarfs and black holes? And when I say black holes, I also mean neutron stars, because it's very similar in terms of the self-lensing parameter space. So if you look back at the roadmap here, like I said, for the black hole part, they're more massive and they're tiny, so they don't eclipse the white dwarf at all. In this case, the duty cycle is much bigger. You have much better chance of being edge on. You have much better chance of catching the flares. So, and the flares can possibly be a lot stronger, right? You can have these big magnifications. So in general, there could be, and these are really fast things. So this is what attracted me to this project to begin with, because of the whole concept of these fast changing things that, within a few minutes, you brighten up to, ×2 brightness and then fall back within 10 seconds. It's like a crazy event. And you have to know what you're looking for, because in most of our surveys, we have exposure times of 30 seconds, and then we take an image and then we come back the next night. We usually don't sit on one target with one telescope and take images really, really quickly so we can see the thing rising and decaying. And this connects to the project I was working on in my PhD, where we had this telescope that was taking really fast images, 25 times per second, and we could see these things. So this is the most exciting part for me, because if any of these systems exist and it's close enough to us for us to actually identify that it's a white dwarf, then it's going to be a weird thing that maybe people haven't looked at. So, it's conceivable that other surveys have missed this just because the flares are so short, okay, and the period is so short that you don't even understand what you're looking at. So one of the things I want to look for is these very fast things that are periodic, and there might be a way to find these things. So I'm not super hopeful, because again, if I do the back of the envelope calculation, if the white dwarf are very rare, right? So black holes are definitely going to be more rare, just because they're more massive. They must be more rare than the white dwarfs, unless there's a giant surprise and we're all going to be shocked that there are more black holes than white dwarf binaries, which nobody thinks that can happen, right? Probably the white dwarf black hole binaries are much more rare than the double white dwarfs. But they're also easier to detect, so there's kind of an offset between those two, and it's more of a high risk, high reward sort of project. So it's going to be much more interesting to find a white dwarf and a black hole in a binary, but it's also probably going to be much more challenging. And here it's the same sort of plot. It shows you the effective volume for the different surveys. But again, I cannot draw a line like this that tells you what the expected number of black hole white dwarf binaries are, because nobody knows. Nobody has a guess yet. So, but I can tell you what is the flare duration. And here you can see that the flare, for where we're most sensitive, the flare takes about 10 or 30 seconds. So we're looking for very, very short flares. I think this is cool. I definitely want to look for this with the new types of surveys that we have, like the curious array of satellites. That should be really fun to see this sort of thing with these telescopes. Yeah, so that's it. Self-lensing, super interesting project, I think. Can tell you a lot about the population of white dwarfs and black holes. If you detect any of them, they're gold-plated events because of the periodicity. You can verify them. You could measure almost everything about the system. The surveys that we're using now, which are sparse, have a pretty low probability of finding them. And even if LSST finds them, it's not going to know which of these flares are actually self-lensing and which of them are other sorts of just transient events. Yeah, there are other ways to try to increase the sensitivity. There are a lot of other avenues that I'm thinking about right now. But yeah, probably what we'll need is a survey that covers a lot of the sky continuously. So you can actually see the flare multiple times on the same system. Is probably our best hope for this thing. Thank you.
So let me ask a few questions.
Sure.
I understand that there are a lot of binary red dwarfs in the universe or in our galaxy, because those are more common than our sun being a singular element. So when these binary red dwarfs,
white dwarfs,
red dwarfs degrade into white dwarfs, right? So there's more chance of having binary white dwarfs because they came from the red dwarfs.
Right. So red dwarfs actually probably will not turn into white dwarfs at all, because red dwarfs are the least massive main sequence stars. And because the more massive a star is, the faster it goes through its fuel, which is kind of counterintuitive. So the most massive stars live for like 1 million years or 10 million years and blow up. The medium stars, like our sun, they will take a few billion years, and then they will turn into a red giant and go down into a white dwarf in the end. And the red dwarf stars, because they're very small, they burn their fuel very, very slowly. So even though they have less mass than the sun, it's going to take hundreds of billions of years, and none of them actually turn into white dwarfs yet.
Oh, I see. Okay, so when you say there are binary white dwarfs, what is your estimate of how much of that you can have in the system? I mean,
so if you're asking how many double white dwarfs are in the galaxy,
yes.
Yes. Okay. So there are a lot of papers on this, because people have measured these systems. Usually what they do is they take either very distant white dwarf pairs and they can measure them separately, or they take very close ones where they're either eclipsing each other, or you can measure that they have velocity, because when they move around each other, one is moving towards you and one is moving away from you. So you can use a Doppler effect. When you measure the spectrum multiple times, you can see that it's rotating. And again, this is a periodic thing. So that's how you know that there's a different period. So there have been a lot of work on white dwarfs and double white dwarfs. And the best estimate right now is that for every 10 white dwarfs in the galaxy, one is a binary where there are 2 white dwarfs orbiting each other. So it's like a 10% binarity fraction. That, of course, changes with the distance between them. But it's about 10%. And there's 1 white dwarf for every 200 parsec cube. So it depends on how far away in the galaxy you want to see. So there are billions of them in the galaxy, but because they're pretty small objects and you cannot see them very, very far, depending on how big your telescope is. So one of the advantages of LSST is that it can see white dwarfs much, much further into the galaxy. So it's going to be exposed to a lot more population of white dwarfs than, for example, TESS. In TESS, you can see about, depending on how precise you want to get, but for good measurements, you have like 4,000 white dwarfs that you can look at with a TESS. So in that population, there's going to be like 400 binaries, and most of them are not going to be agile.
Oh, so there's still quite a few. Okay.
Yeah, I mean, once you start looking at populations of stars, it's big numbers, right? It's astronomical numbers. But if you think about this, there are 200 or 500 billion stars in the galaxy. And then with TESS, you can see 4,000 of them. That's actually a tiny fraction. It's not a lot. It's not a big statistical sample, right? I think that the number right now, the paper that I'm using to identify white dwarfs, used the Gaia satellite, and they identified about 1 million white dwarfs that they're pretty confident that they are white dwarfs. So that tells you about, if you want to know, for example, how many white dwarfs we know that are white dwarfs, then it's about 1 million.
Yeah, so a
Not a
million,
giant number.
so 100,000 would be a binary white dwarf.
Yeah, something like that.
And then, and I understand that the instruments are not good enough to really help you find them. So you are now targeting white dwarf and black hole binaries.
Right. So I'm looking for all of them. I'm going to try to search for both these classes of objects, but I'll put it this way: the double white dwarfs I will look for in existing surveys, but I know that statistically I'm probably not going to find anything. I'm still going to look just to make sure. And for double white dwarf, for white dwarf black hole or white dwarf neutron star, I cannot know in advance that I will not find anything, but it's very, very likely that I will not find anything just because of statistics.
Yeah, because of the very short duration, so you'll be able to capture it.
I think I can. I think the durations I can probably, if I use the right algorithms and I look in the right places, I can probably be okay with the durations. I just think that these systems are intrinsically much more rare. So if you have a 10% chance of a white dwarf having a white dwarf companion, it's got to be at least 100 times more rare to have a black hole.
Oh yeah.
I'm just guessing, right? I don't actually know the number, but
Yeah,
I mean,
that's
just
what you're
because
trying to find. Yeah.
I mean, just if you look at how, because black holes come from stars that are more massive, that there will be like 8 solar mass stars when they start out to make the smallest black holes. And white dwarfs come from 1 solar mass stars like our sun. So more massive stars are just much more rare to begin with. And to get them in this configuration where they're in a binary, in a close binary, and they have to be in a close orbit with the white dwarfs. So it's kind of like, I don't actually know. Nobody knows the population numbers, but it's got to be lower. I mean, dramatically lower. So that's why I'm not very hopeful that I can find these things with existing technology. But who knows? If you have a deep survey that takes images very rapidly, maybe if you look at enough white dwarfs, you will start to see these systems. I think it's I think mostly I'm interested. I think that the biggest result of this paper is the roadmap. Kind of tells you which part of the parameter space you can look at and which you can't, and so it's I think that for future surveys that's going to be a very useful thing.
So if you find a pair, luckily on black hole and white dwarf, then you can, I guess, study them and see and learn from that. That's kind of the goal once you find them.
Yeah, I mean, for example, if you find one of these black holes orbiting a white dwarf, then you can say something about how many black holes and white dwarfs are in pair. And that I cannot say that now because nobody knows. All you have are, like simulations based people like do population simulation of stars in the galaxy and try to figure out what happens to them in the end. But these are all guesses. These models are not constrained by anything that we've measured. So if you even have one system, that already constrains your problem by a lot.
So your challenge is a little bit similar to Casey. Casey was trying to find rogue black hole or neutron star by itself, which is very hard.
Yeah.
And you're trying to find a pair that's also extremely hard. Nobody has found that yet. Is that true?
Well, finding black holes is hard.
Yes. Well, she find one black hole or a neutron star, based on
yes. Yeah, it's very hard to tell them apart as well.
Yeah.
But yeah, these are things that by definition don't emit anything by themselves. So for astronomers, that's a big challenge, and you kind of have to find these clever ways using gravitational lensing and stuff like that to know what's going on.
So just in comparison, you are trying to find a pair that nobody has found before.
Yeah. So Casey's looking for she wants to be lucky enough to see the black hole lensing some random star in the background.
Yes.
And I'm waiting to be lucky for that black hole to just by chance to be orbiting with a white dwarf. And then the white dwarf will tell me that there's a black hole next to it. So you kind of have to piggyback off some other light source to tell you there's a black hole there, because the black hole is not going to tell you that by itself.
Okay, we wish you success, because that would be a first, at least for humanity, to find that, right? Yeah.
Hey, one question.
Sure.
So, like you say, you have to look at the right places. Okay. So the thing is, there are billions and billions of stars. So, is there some based on intuition, or is there some sort of algorithm that lead you to look at any particular place for the phenomena that you want to identify?
Right. So one of the decisions I made early on is that I'm not going to be looking at regular stars, what you call main sequence stars. And there are many more main sequence stars. They're brighter. You can see them much further away than white dwarfs. But because of just the sizes in the system, I decided that I'm going to concentrate on the white dwarf sources. So that immediately means there's many fewer stars to look at to begin with. So there's about 1 million white dwarfs that we know about. That's the catalog that I'm looking at. And then out of those white dwarfs, I can only look at the ones that have been actually observed by the different surveys. So, for example, TESS has very small aperture, so it doesn't see very deep into space. It only sees white dwarfs that are very close to us. The ZTF survey can look a little bit further. It's got bigger aperture. So basically, the map that I'm using is the catalog of white dwarfs. So I'm first of all looking only at them. So that narrows down the number of stars I have to look at and makes my job a lot easier because I only have to look at data from white dwarfs. On the other hand, that kind of narrows down the search that I can do. So if I'm not lucky that one of these white dwarfs is self-lensing, then there's nothing I can do. There's only a small number of white dwarfs that I can look at. So it's a blessing and it's a curse. Now, in the future, I might conceivably do something where I look for main sequence stars, maybe look at the red dwarfs, which are smaller, and then maybe some of these flares can be visible. I haven't really looked at that. I've been concentrating on the white dwarf part of the space, but yeah, maybe. Right now, as long as it's white dwarfs, it's a smaller data set, so it's easier to process as well.
Your data set is only for our own galaxy, right?
Yes.
Yeah, because you have to be closer. Okay. All right.
Yeah, there's a lot of stuff that we can do today with stellar astronomy. So looking at stars in our galaxy because of the Gaia satellite. It's an ESA mission, European Space Agency, and it's been very successful. It's basically mapped out the position and the distance and the colors of billions of stars in our galaxy. And using that map, you can do all sorts of things like identify 1 million white dwarfs. So now you know where they are and you can look at them. And it's kind of revived in the last few years the interest of people in stuff inside our galaxy. So I think that's cool. I think it's a good time to be researching stars.
So would the Rubin Observatory by Dean Kahn help your search?
Which one? The Rubin Observatory?
New Rubin Observatory that's coming online. It's not here yet.
Yes, so I was talking about LSST. That they used to call it LSST. Now they call it Rubin, the Vera Rubin survey.
Yeah. LSST, correct. It's the same.
It's the same thing. So everybody in astronomy is waiting for LSST, right? Everybody's saying when LSST comes, then we can finally do all the miracles that we talked about. So I'm kind of I'm a little embarrassed to put that in the paper. Like you kind of see it in every scientific paper where you don't find anything, and they say when LSST comes online, we'll find all these things. So
it's coming on next year, I think.
Oh, they've been saying that for a while now.
Yeah.
I hope in the next year or two it's probably gonna it will work.
Okay, great.